In order to model this Savonius VAWT in SimScale, first of all, need to generate an IGES or STEP file in any CAD program. So I've already previously generated a vertical axis wind turbine Savonius with a semicircular profile. So once you go to the website, I've already posted the website address on the description. I also posted a video which will help with a quick way to understand SimScale and use it for your own analysis in order to understand what SimScale can do. Before you can actually use SimScale online, you'll need to register, and the developers are also going to provide you some helpful tips on how to use it. You may not have so much time to read everything because you are just testing, but that video tutorial will really help you to understand how to go about testing SimScale for this vertical axis wind turbine exercise. So the first thing is to import the IGES or the step file, which I already have here from a CAD program. So it's just basically the body parts that are important to you that you use for the import. So once it's imported, you will need to edit it. In this case, I've not done any major editing aside what was done in that previous video. So what was edited is the airfoil, the air flowing around this Savonius VAWT. So you can watch it on the screen now. So this is creating a boundary for the air pressure that is flowing around the VAWT system itself. So once this air pressure, the boundary has been created, you'll be able to know how far the air is going from one point to another. Let me just give you a hint. It's possible to actually validate this on site by, for example, if you are using a wind tunnel, if you actually apply pressure or wind to the Savonius VAWT, you will see the point where the wind is largest at the wake. You can then take your sensors to pick up the value at that point to know whether it tallies with the value in CFD. Because when the wind hits one part of the wind turbine, it diverts all the wind to a certain direction, but there's a point in that direction that is maximum. Once we get to that area in this video, I'm going to point it for you to see how practical CFD can be made in the field or in the wind tunnel lab. So there are times when you have some conflict with the drawing that was generated, in which case I was having some conflict with the bottom part. So I had to delete it directly so that it doesn't cause any issues, because some of these parts in the real sense, they are not moving, they are static parts, and these static parts can be designed for moment and stresses as a static element. So it doesn't necessarily require lift and drag in the elaborate sense in the way that the Savonius profile will require. So we define the external body and accept certain values and move ahead to Boolean operation, which is to subtract in order to obtain the air that is flowing around the VAWT. So here we are going to perform the Boolean operation. In which case we are going to subtract. click on apply. Once it applies, if there is no error, then you need to go ahead and delete those singular. So once there is no error and the intersection has been done, you need to go and delete all of those model parts, because you are going to get an error if it is not done. The flow region that has been subtracted contains both the air volume and the airfoil, the profile of the Savonius VAWT together. You can see that highlighting the flow region is actually showing the Savonius VAWT inside, even though you deleted the individual profiles of the VAWT. So that will prevent you from having any errors. So we save. Once you save, it takes you down to this page where you select create simulation. So once you create simulation, you can then select it as an incompressible fluid. I wanted to select other options, but let's make it simple. Just incompressible fluid, and the fluid is air, which is flowing around the Savonius VAWT. So the help file that will be sent by the developer will help you to be able to utilize to the max SimScale. So you will utilize all of its functionalities. But yeah, this is just a quick tutorial so that one knows how to use SimScale for simulating CFD and FEA. So the materials for the incompressible fluid is air. We select air and apply. The next thing is going to be the wind speed, the boundary conditions. So the boundary conditions and the wind speed are the inlet and are the outlet. So the inlet is positive X direction. So these are the values we used for this simulation. 11 meters per second. So once the velocity has been included, the next thing is the pressure of the wall at the back, which we are going to highlight. And so once the velocity has been imputed at the inlet of this flow volume, at the outlet you are going to have the pressure volume. So once the inlet velocity has been specified, at the outlet you are going to specify a pressure of 0, similar to that tutorial. So let's just follow it accordingly and see the outcome for this analysis. You can always go back once you have a full understanding of SimScale. You can then go ahead and run a more elaborate analysis. So I'm making all the other walls to be slip walls prior to the analysis. So once all of this is accepted, it's then possible. You can always adjust mesh, but it will take time. So, but this is because this is a quick tutorial adjusting the mesh. I adjusted the mesh earlier during some trials, and it took quite a long time. So we'll just take the default in the system, and then we'll go ahead and run this analysis. Okay, we specify forces and moments that you require in terms of the outputted results. And the forces and moments are going to be computed. So So that's for FEA. So in which case you're having CFD on one side and FEA on the other side. So these are a selection of the settings. Next, we're going to run the simulation. You can give it any name. So you see here 6 to 22 minutes, how long it's going to take. So at the end of the simulation, you can then post-process the results. Once you click on post-processing, the first information that comes up are different cutting planes in different directions. It will be X, Y, or Z. So they started out as Y, so I switched it to Z so that you can have an information of how the wind speed spreads in the horizontal plane. So these values now are the wind speed, how it flows over the Savonius profile. So you can see how the wind builds up from 11 meters or 12 meters per second and going all the way to about 14 meters per second in some cases. So there's usually a build up. So I've removed the external boundary of the air volume so that we can see the object of analysis much clearer. Again, that can be found in the tutorial. So this is the Z direction of the wind speed, so you can see how the wind diverts, in which case I'm saying that from this you'll be able to understand where the wind is going to be largest behind the VAWTs, so that you can then test it in the field or in the wind tunnel to validate what has been done in CFD. You should be getting similar values compared to what you have here on the CFD. So that's what I explained at the beginning of this video. So changing the path column from velocity to pressure is how you'll be able to see the pressure effects on the wind turbine profile. So you can see here the pressure on it. Close to the edges and at the mid sections you have heavy stresses acting on this wind turbine profile. So from here, just as it was done in that tutorial, we're going to see how the flow volume of air relates or interacts with this Savonius VAWT profile. We're going to see how it was done in this case. So because this is an internet-based application, sometimes the internet makes it slow a bit. So it depends on how fast the internet services are, but for mine it was a little challenge during this video editing session. So this is just analyzing the different forces that are acting on this semicircular profile. So you can see forces, you can see pressure in the different directions, X, Y, and Z direction, both maximum and minimum. You can see all of these values here. So here now is particle tracing to see how the air profile flows around the Savonius VAWT profile. So you have to pick it from the inlet of air into this air volume. But initially when I did it the first time, I picked a point that was at the outlet of the flow volume. So once I hid all the other objects, I was not able to see the airflow around the Savonius. So I had to switch it around. I turned the model around to the right X direction. And when I used this particle tracing again, it showed the airflow around the Savonius profile. So you can see it's not showing any airflow around the wind turbine system. So when I now checked with the cross-sectional pressures, that's when I realized that the wind speed was dropping before the wind turbine system. Hence, it confirmed that the orientation of the wind turbine system was not what was being expected, meaning that the inlet was on the other side. So it was switched back, and then the particle tracing was tried again, in which case you'll be able to see the outcome. So after hiding the external flow volume, you can then see the air pressure and the air interaction with the vertical axis wind turbine. Thank you for watching this video. This is Catchment of Resources, where we create for better living.